Okay, so we've got this equation of motion. We can do some simplifications here and drop some terms that are small due to the fact that we're looking at the small perturbations in the roll angle. Okay, so we've got this thing in terms of the roll angle here on the left hand side, but we have v squared, r squared terms, and those are functions of delta, this front and the rear steer, which we previously determined. And V and R for small deltas, small steer, they are going to be treated as small angles. So an R squared times a theta that's small, we can drop that whole term. That is a small term relative to the others. And then this V squared times theta is also going to be able to be dropped because delta R and delta F are small in addition to theta. So we can drop those, and then we just have I1 plus mh squared theta double dot minus mgh theta equals negative mh v dot plus ru. Alright, so this is an equation that we are going to move forward with. We have a simple linear equation that describes the system. And a few things to note. This left-hand side describes a compound pendulum. And you've probably seen that in your other classes, and we'll look at that a little more closely in a second. And then this side looks like mh times, right, this looks like something we know, the lateral acceleration, body fixed to I prime, j hat prime, k hat prime. That's how we had that defined for u and v, which were both in those directions there. Okay, so we have a force on the right hand side that's equivalently a torque in this case, m times h will give us h times ACC times m is going to give us a torque, but it comes from whatever lateral acceleration you have at this point P that's in the ground plane, and that will generate a torque that then will cause the left hand side to do some kind of motion with respect to the roll angle. All right. If we plug in our expressions for V and R, then we can write this equation like so. So interestingly, we have delta F, delta R, and each of their derivatives in the right-hand side here. So giving a specified steer, front or rear steer angle, we could then specify its derivative And giving both of those, we can then calculate what kind of torque is acting on this system to keep the roll angle, to control the roll angle, right? So we have steer angle for front and rear inputs here that are going to cause some roll angle motion. All right, so this is our single degree of freedom equation of motion, and it is linear. So I want to speak one last thing. So that left-hand side I mentioned, it looks like a compound pendulum. You've probably seen if I have theta, and this is m and some I, and there's a mg force acting on this system, then the equations of motion end up being I plus m, got that, some length of the pendulum, L squared, theta double dot, minus mgh theta. And then if we imagine some kind of torque acting here, an arbitrary torque that we apply to try to make that pendulum move, that would equal the sum of the torques on the system, and it would be that single torque. This is a compound pendulum equation, and this inertial term here is the inertia about the pin joint instead of about the center of mass of this arbitrary object that has some inertia that's determined by the parallel axis theorem. So we have we have this equation. We basically have the equation for an inverted pendulum that represents this bicycle body, and our torque that's going to make it control the roll angle is governed by the deltas, right? And how fast you're going, and then some information about the geometry and mass of the vehicle. So a few conclusions that we get from this equation of motion. An inverted compound pendulum is unstable. And we can see that because the negative mgh theta term, that negative mgh is always negative. So the only way that it isn't negative is if the pendulum is not inverted, right? So a pendulum that was pointing downwards would have a positive term there, and we'd have a stable system. Okay, and then the inertial term is always positive, but we have an inherently unstable system. So I told you that bicycles or motorcycles can be self-stable at some times. It's impossible for this model to be stable. That negative mgh term is always negative, and we don't have a stable system. So this model is not sufficient enough, to capture the bicycle motorcycle self-stability that I showed you some experimental videos of, and we demonstrated live too. Alright, so that's potentially okay. If we do not steer, right, if we set all the deltas equal to 0, then bicycle falls over. There's no way to control a roll angle if you don't have steer. There's no terms over there that are going to help anything. So set the right hand side to 0 effectively. We just have that simple inverted pendulum, and any perturbation, it'll fall. And then lastly, if you think about U, That's the forward speed of this vehicle. We have u and u squared in the right-hand side of this equation. If we look at when u goes to 0, right, the slower and slower we are proceeding, then it's hard. The ability for the steer to produce a large torque goes down. Okay, so we can't produce a riding torque at low speeds, right? And as it hits 0, we also have a 0 in the right-hand terms. We can't do anything with that right-hand side. And then we can also think about, well, what if u is large? Well, this means that for very small steer inputs, if we have a multiplied by these big u squareds, we're going to have a huge torque. Okay, so this system is going to become more sensitive to steer as u increases. More sensitive. So you can generate large torques with little steer. As speed increases. Okay, so that's the equation of motion, and a little bit of thinking about it. And we're going to take that now in the next video, turn it into some transfer functions, and think about control aspects.